Hi everyone, and welcome to part 3 of this formal logic video series. In this session we're going to look at how we can construct basic proofs in PL. So what I'll do first is just go through the rules of inference that we'll be using in constructing our proofs, and the rules that I'll look at are conjunction introduction, conjunction elimination, negation elimination, disjunction introduction, conditional elimination, and biconditional elimination. And then once I've done that, I'll go through 4 basic proofs so that we can see these rules being put into use. Now the use of a proof in PL is that it's going to allow us to show that certain formulas can be derived from certain other formulas. So far what we've done, if we had a sequent like this, A then B, A, therefore B. So far we've used this symbol, which is the semantic turnstile, and that means that B follows logically from the meaning of A, then B, and A. And we could construct a truth table to show that. So using the kind of standard layout for a truth table of A and B, we'd end up with something like this. And as we know, we can look at this table and see that there's actually only one case in which all the premises are true, and in that case the conclusion is also true. So this turns out to be deductively valid because it's impossible for this argument's premises to be true and its conclusion to be false. Now what we're going to do is construct a proof. So we'll have something that looks a little like this, and we'll use rules of inference to show that B can be derived from these two premises. But first we need to know some rules in order to know which steps we can make and what we can introduce here. At the moment all we've got are premises. Okay, on to the rules. So we're just going to look at 6 rules in this session, and they're quite basic rules, so they shouldn't be too hard to pick up, and we'll look at some more complicated ones in the next few sessions. So starting with our conjunction, introduction and elimination, these are really very simple rules. So these rules say that if we have phi and we have psi on a scope bar, then anywhere underneath there we can write phi and psi, like that. And all we need to do to justify the introduction of this conjunctive statement is cite the 2 lines of proof on which both conjuncts occur, and then our conjunction introduction rule here. Now of course I've written it this way round. The phi comes first, and here's the phi first in our formula, psi comes second. But of course I could have written just as easily the conjunction the other way round. So we could have had psi and phi this way round, and we would have cited exactly the same justification, so the same 2 lines and the same rule. And we could have had the formula that comes after phi, so the second formula on our scope bar in numerical order, coming first in our conjunction. This rule allows us to introduce it either way round. Okay. So the flip side of this rule is the conjunction elimination. So if we have phi and psi on our scope bar, that means that anywhere below that we can write either of those conjuncts in isolation of one another. So here we've got a conjunction statement that links the formula phi with the formula psi, and because we've got that, this is stating both of those are true in conjunction. Well, we can infer from that that phi is true, and we'll just cite line 1 and our conjunction elimination rule, and also that psi is true, and they're true in isolation of one another if they're true in conjunction. And these track a very basic inference that we might make. Of course, if phi is true and psi is true, then the conjunction of phi and psi is true. Of course, if the conjunction of phi and psi is true, then phi is true individually and psi is true individually. These are just very basic assumptions, and what we're doing really is introducing them into our system of proof so that we can make use of those inferences in a formal system. Okay, moving on. The next rule, again, tracks an intuitive notion that many of you will have picked up on already when we were looking at well-formed formulas. So, if we have not phi, then anywhere below that on the same scope bar we can write phi, and all we need to do is write the line number and our negation elimination rule. Now this is again an obvious inference. Some of you will have thought when we were looking at well-formed formulas, well, if we have not A, surely that just means the same as A. Or if we had not A, surely that just means the same as not A. In other words, two negations seem to cancel each other out. And that's exactly right, and that's the rule that we're constructing to use in our proofs. If we have two negations, we'll just cancel them out. But notice we can only do two at a time. Right, this doesn't say if we have four negations we can reduce it just to the well-formed formula. We have to do just two steps at a time. Okay. So next is perhaps the easiest rule that we'll look at, although perhaps sometimes a little confusing and easy to forget. If you have any well-formed formula, here phi on your scope bar, then you're justified in writing phi or psi, where psi is any other well-formed formula. And all we need to do to justify that move is cite the line on which phi occurred and disjunction introduction state our rule. And we could also, so in this case the disjunction stems from our knowing that phi, and we add on or psi. We could have also had psi coming first. Just in the same way with the conjunction, it could occur either way round. So too here, although we're starting from phi, phi can occur second in our disjunctive statement, and we just use exactly the same rule, 1 and disjunction introduction. Okay, so if we know that phi then psi, and we know that phi, the conditional elimination rule tells us that anywhere below these two statements on a scope bar we can write psi. We just need to cite the line with the conditional statement and then the line that has the antecedent of that conditional statement on it, and our conditional elimination rule. So remember that every conditional statement is composed of an antecedent and a consequent. And a conditional statement is sometimes expressed as saying that this would be expressed as phi implies psi, right? The antecedent implies the consequent or entails the consequent in some way. So if we know a conditional statement and we know its antecedent, then of course we can derive its consequent because the antecedent implies that consequent. So phi then psi, phi therefore psi, and again our rule will just be to cite both of these lines and the conditional elimination rule. Now bear in mind that this only goes one way. Right? We can only get the consequent by having the antecedent. If we'd have had phi then psi, and on line 2 we'd had psi, we're not justified in writing phi, right? We can't get the consequent, and therefore we can't have the consequent in this conditional statement and thereby derive the antecedent, right? This isn't a valid form of reasoning, as we've already seen. This actually commits the fallacy of affirming the consequent, which you'll have looked at in critical thinking. Okay, so phi then psi, phi, we can derive psi. Now the biconditional elimination rule is very similar to the conditional elimination rule. If we have phi, if and only if psi, and we have phi, then we can derive psi. And again we'll need two lines of justification, 1 and 2, and our biconditional elimination rule. But whereas the conditional statement can only go one way, a biconditional goes both ways, right? It's a biconditional. It's really expressing phi entails psi and psi entails phi. Right? These two are logically equivalent, so if one is true then the other is. So that means that if we knew psi, then we would be able to derive phi. So here I'll leave phi here, but just show that we could have used, if we had phi on line 3, we could use 1 and 3 to derive phi here, using our biconditional elimination rule. So again, with the conditional statement, we can only go from antecedent to consequent. We need the antecedent in order to derive anything from this kind of statement. With a biconditional, if you have either side of this, then you can derive the other. So if you have phi, you can derive psi, and if you have psi, you can derive phi using this statement. So now with our very basic sequence, A then B, A, therefore B, this only requires one step, but we can now see that on line 3 we could write B, and we could cite our conditional elimination rule, 1, 2, and conditional elimination. And so this is a way, we've shown here that we can derive B from this using rules of inference in PL, and rather than using this semantic turnstile, we'd express that in the following way. A then B, A. Again, we have this sign that translates roughly as therefore for B. And what this says is that B is derivable from A then B and A. Okay, so let's look at some examples of these rules in action. So here is a sequence for us to prove. We've got two formulas, not A and B, and A and C or B, then F, and from that we need to deduce A and F. So this statement says that A and F can be derived from these two formulas, and in proving this sequence, what we're going to do is construct a proof that shows that A and F are derivable from these formulas. So in constructing a proof, first of all we'll start off with, we've got a scope bar here, and this is where all the work's going to be done. The first thing that we'll do is add in our premises. So everything on the left hand side of this turnstile, our syntactic turnstile, we'll treat as premises. So we've got 1, not A and B, and we've got 2, A and C, or B, then F. And we'll label those over here as our premises. So it's important to make a habit of labeling everything that we do, all the steps in our proof. The proof isn't complete unless we've got our justifications for each line of the proof on our right hand side, telling us why it is that these are here. With these two it's fine, they're just premises, so we don't need any further justification other than the fact that they're our starting point. Okay, and then next what I'm going to do is I'm going to put a Z here at the bottom and write in what we're working towards. So down here I'll put A and F. So this is the conclusion that our proof is aiming at. Now I label this Z rather than a number because I don't know yet how long this proof is going to turn out to be. It could be 5 steps, it could be 20. By labeling it Z just means that I've got something to refer to. Line Z can come in some of my justifications as I work through, but I don't need to worry about which number it is exactly. Okay, so then we need a method for doing this proof. We need to get from these premises, using those rules that we've got, to our conclusion. And the general advice is to begin by working backwards through the proof. And what that means is to think, okay, here is my conclusion, how might I have arrived at this? So the first question we'll ask is, what rule would have been written here next to in the justification for our conclusion? Now just having a look at this, it looks like this will have been introduced with a conjunction introduction, right? The main operator of this formula is a conjunction, so we can be safe in assuming that this was a conjunction introduction. Where would we have gotten this from? Well, we would have needed A and F. So we'll label those lines X and Y, and we'll say that we inferred A and F, the conjunction of A and F, from A on line X and Y on line F. Okay, and again, now what we can do is just work backwards once more. So our question now becomes, well, what would be the justification that goes here next to F? How would we have gotten F? And this is where we're going to need to look at our premises and think, what could we get from these? What could these kinds of premises produce? Well, look, we want to derive an F, and up here we've got F as the consequent of a conditional statement, A and C, or B, then F. So if we could get A and C or B, then we could derive F, which is what we want. So it looks like we're going to have a conditional elimination, and that's going to be from line 2, and again let's add in a letter, line W, and on line W we'll say that we had A and C or B. In fact, I only need one bracket there. Okay, so we'll say that 2 and W gave us F. Now our next thought might be, well, where could we could either now carry on with this line of thought, think how did we produce this, or we could switch to say, well, we'll now work out line X. What I'm going to do is just stick with this line of thought. I'm going to work out how we could get to F as far as I possibly can, and then I'm going to switch to A. So how could we have gotten A and C or B, right? What's the justification that's going to go in this space? Now the main operator of this formula is a disjunction, so presumably this will have been introduced via a disjunction introduction, and we would have introduced it from a line above on which there'd be either one of the disjuncts. So now our thought could be, well, which one would we be able to get more easily? We've got A and C, or we could have B. Well, looking again at our premises, we're not going to be able to use this conditional statement because remember, we're trying to derive the antecedent of this. So we're not going to get the antecedent from the conditional statement itself. In our first sentence, our first formula on line 1, we've got both A and B, but no C. So arriving at A and C looks like it's going to be impossible. But we could get B, and once we have B, we can use a disjunction introduction to get this whole statement. So, again, I'm going to write a little V here, and I'm going to say that this was introduced by line V and a disjunction introduction, and on line V I'm going to write B. Okay, again, I'm just sticking. I'm going to return to the A in a moment, but looking at this, it looks like we're going to get the A and B at exactly the same time. So, by working back and just looking at the B side of things, hopefully I'll be able to fill in the justification on line X for our introducing A when I'm able to do the same for introducing B. So, how would we have gotten B? Right, again, let's ask this question. What would I need to write here on this line? Well, if we look at our premises, we've got this conditional statement. So if we could somehow get A and B out on this line, on line U, then we could do U conjunction elimination. How would we get this line? Well, look, we've got two negations here, and as we know, when we've got two negations right next to each other, they cancel each other out. So we could arrive at line U from line 1 and a negation elimination. And there we go. Now, although they're a bit further apart, let's move this up. And we'll see we've joined up our premises and conclusion. We've met in the middle. So from not A, we derived A and B, and from that we got B, but we also get A, so we can now fill in this line. So we got that also from U and a conjunction elimination. From B, we used a disjunction introduction to get A and C, and then from there we used A and C or B with our conditional statement to derive F. So that's 2 line W, we derived F, and then from X and Y we derived A and F. And there's the end of our proof. All that's left to do is just go through and renumber these. So to get rid of our letters and number them properly instead. So 3, 4, 5, 6, 7, 8, and we're going to need to rewrite a little here. Let's get rid of all of that. So A and B we got from there. B we got from 3 and a conjunction elimination. A and C or B, we did a disjunction introduction of 4. Remember, we don't need any justification beyond the fact that B is true. If B is true, then A and C or B is true. A again we got from 3 and a conjunction elimination. F we got from 2 and 5 and a conditional elimination. Now, a brief note here is that I always number the lines of the proof in numerical order. So even though we might think, look, maybe it makes more sense to say the antecedent, we have the antecedent first and then the conditional statement itself, or suppose that we later had a conditional statement and earlier on, higher up, we had the antecedent, I just always would number them in numerical order, just as a convention. Okay, and then finally, our conclusion, A and F, we got from lines 6 and 7, and a conjunction introduction. And there we go, there's our first proof completed. Let's have a look at the second one. So again, my first step is going to be to write in my premises. So again, I've got 2 here as before. On line 1 I can write f and not g, and I'll mark that as a premise. On line 2 I can write g or w and g or u, then z, again that's a premise, and then right down at the bottom, as I did before, I'm going to write my conclusion in. I'm going to number it z. So f and z and not g. And I'm going to go through exactly the same process. I'm going to start at the bottom and think, what would my justification have been for introducing z, the formula on line z? Well, the rule that I would have used looks to be, again, a conjunction introduction, being that this conjunction here is the main operator of this formula. Now, where will that have come from? Well, once again, we're going to say on line x and line y, we will have had the 2 conjuncts, so x, f, and z. Don't need that bracket, in fact. And on y, not g. So from there, we just need to think, where could we have gotten these formulas from? And here again, it's useful, I think, to, although we're working back up through the formula, through the proof, sorry, we also need to have in mind about what we could create from this. What kinds of things these premises could give to us on these few lines. Well, the first thing to notice is that not g can be derived straight away. Should put x and y there. Not g can be derived straight away from line 1, f and not g. So if we cite line 1 and a conjunction elimination, that gives us g. So that's fine, we've already sorted out 1/2 of this. Now what about f and z? Well, it looks like this is going to be another conjunction introduction, as a conjunction is the main operator, so conjunction introduction. And that means that on lines v and w, I'm going to need z and I'm going to need f. So, where are these 2 things going to come from? Well, z is the consequent of this conditional statement on line 2. We've got z here, and that's what we're looking to get here. So presumably we'll use a conditional elimination to get that. We'll be using line 2 and then another line. F is a little bit simpler. We get that from the same conjunction that we got not g from. So conjunction elimination of 1 gives us that. Now, for our conditional elimination, we're going to need another line, so line u, on which we'll have g or w and, sorry, I should have another bracket around it, g or w and g or u. Don't need that bracket there. Okay, so where are we going to get these 2 things from, right? What could have introduced this? Well, again, another conjunction introduction, so that means on lines S and T we're going to need G or W and G or U. So we'll say that from S and T we used a conjunction conjunction introduction to get this. Where could these have come from? Well, let's look again at our premises. These look like they're both going to have been introduced with a disjunction introduction, being that that's the main formula. So we would need one of the disjuncts, and the one that's in common is G. So if we had G, we could introduce both of these. And looking at our premises, it's not going to come from this conditional, because remember, we're trying to get the antecedent of this conditional. in F and not G, it looks like we might be able to get G. And how would we do that? Well, if on line 3 we put not G, and that is a conjunction elimination from 1, on line 4 we could just write G with a negation elimination of 3. And from there it's really easy. Now we can say, well, G or W, well, that's just a disjunction introduction from 4, and G or U again is a disjunction introduction from 4. So there again we've built our proof up from the bottom until it meets the work that we're doing down from the premises. Let's move that up. And again, all that remains now is for me to go through and renumber this proof. So 4, 5, 6, 7, 8, 9, 10, 11, 12. And then just rewriting my rules. Let's take account of that. So this was a conjunction introduction of 5 and 6. This was a conjunction elimination of number 1, so 1 conjunction elimination. Z was from line 2, our conditional statement, and here we've got the antecedent of that statement, so that's line 2 and line 7. F and Z is 8 and 9. And also I've gotten rid of this symbol here, so that was a conjunction elimination from 1, and then finally we've got F and Z and not G. Well, that's 10 and 11. Okay, and there we go, there's our proof completed. Now notice that on line 3 we've got not G, and we've got the same thing on line 11. Right, we've got a bit of repetition in our proof. Now there's no problem with that. That's come from the fact that we've worked backwards and we've thought, what do we need here? And it turns out that we've needed that thing twice. We've needed it first to construct our antecedent, and then later on as part of our conclusion. Now there's no worry in having two things, something repeat in your proof, but perhaps to make the proof more elegant, what we could do is remove line 11. So we'd only have 11 steps, and instead of citing the previous line 11, what we'll do is say 1 and 10, and a conjunction introduction gives us our final statement. So again, a little bit of rewriting allows us to make the proof a little bit more elegant, less steps, but there's no worry in having repeated information, that's fine. Okay, let's move on to look at the third proof. So in this one, the formulas that we're working with are a little bit longer, but that shouldn't worry us. We shouldn't be worried about it being any more complicated. We've got a set of rules that we can apply mechanically to this in order to derive C and G or A from the formulas on the left-hand side of our syntactic turnstile. And hopefully just by using this process of working back up from the bottom, it doesn't matter how complicated our formulas are up here, we should always have a route back to our premises. So let's have a go. Again, first of all, here I've got 3 formulas before the turnstile, so I get 3 premises. So number 1 is A, if and only if B or C and F or G. And that's a premise, so let's put a P in there. On line 2 I get K, then J, then K, then F, and J, then B. Just 3. And then finally on line 3 we have J and not K. And all 3 of those are premises. And just as before, I'm going to put on line Z our conclusion, which is C and G or A. And I'm just going to use exactly the same process that I used before of working back through the proof to find out how I could derive this from these premises. But again, it's always worth having to mind what we could produce from these premises. What do I mean by that? Well, perhaps something we could do at the very beginning of a proof is just think, well, let's look at premise 3, J and not K. From that I know I could get J and I could get not K. Those would both be conjunction eliminations from line 3. And from not K on line 6 I could write K. That would be a negation elimination of line 5. So now I have J and K. K is the antecedent of this large conditional statement. So I know I'll be able to get on line 7 the consequent J, then K, then F, and J, then B. And I've also got J, so I know I can get this. So on line 8 I can get K, then F, and J, then B. So I've gone quite a few steps through, and all I've done is just think about what I can produce from these 3 premises that we had. What kind of stuff can I get out? Okay, and I need some rules to introduce this. So here on line 7 we've used K and this conditional statement, so line 2 and line 6. 2 and 6 and a conditional elimination, and then on line 8 I've used J, which is line 4, and this conditional on line 7. 4 and 7. Conditional elimination. So just again to reiterate that in each case we saw that we could derive K from this statement J and not K, and that's the antecedent of this conditional. And we also got J from this conditional statement, and J turned out to be the antecedent of this conditional. So we could derive this later statement. So once we've done a little bit of, we can do this partially in our head, or you can write it down if you want, but I think it's worth, although we say work from the bottom up, to really be working from both ends at once, to be mindful about what we've got in our premises and therefore what we could produce and how we could work towards this conclusion, even if we don't know exactly what the middle is going to look like. So now let's look at line Z and think about how we got from these premises and what we've produced here down to Z. And again, we'll start off by thinking, what rule would we have used to introduce this? Well, the main operator is a disjunction, so it looks like a disjunction introduction is going to be a good bet. And to do that, we're going to need one of these 2 disjuncts. So let's have a look at what we've got up here. We don't have C or G through any of this except in this top statement. And we've also got A here, so what we need here on line Y, we need to work out which disjunct we got this from, which is more likely at least. And in this first premise we've got A if and only if, B or C, and F or G. Now I think that makes it look like what we're going to have worked from is A. We're going to have introduced this disjunction from A. Why is that? Well, because suppose that we derive A from this, that's going to allow us to, we're immediately going to be able to use our disjunction introduction rule with line Y to get our conclusion. If we were to go the other way, if we derived B or C and F or G, we'd end up with 2 disjunctive statements, and we don't yet have a rule for disjunction elimination, so it's going to be impossible for us at the moment to get C and G out of those 2 disjunctive statements. So I think that A is our best bet here. And we've already said that A is going to come from this statement on line 1, this biconditional, we'll also use line X and the biconditional elimination rule. So on line X, we'll need to have B or C and F or G. Okay, where is this going to have come from? Well, again, it looks like it's a conjunction introduction of B or C and F or G. So if we say that on lines V and W here, we're going to need B or C and F or G. Okay, now we can think about where these came from, and here again it's going to be useful to look up here at our the stuff that we've worked out from our premises. We're going to have introduced these by disjunction introduction. Right, these are disjunctive statements. So which side are we going to need? So for F or G, what would we have needed here? Well, looking at our premises, especially this one, in fact, let's do a little bit more work from here. We've got K then F and J then B. So from that we can get K then F on its own, this conditional statement. That's from 8, conjunction elimination. And on line 10 we can get J then B. So that would be again from 8 and a conjunction elimination. Now, F and B are both consequence of these conditional statements for which we already have the antecedents, right? The antecedents are K, we've got that, and J. So we know that we can derive F and B. So it looks like it's going to be F and B that we want to see on these two lines. So let's just go ahead and do that. So on line 11 we'll have F, and that's going to have come from 6 and 9, and a conditional elimination. And on line 12 we'll have B, and that's going to have come from 4 and 10. So 4 is J, 10 is J then B, 4 and 10, and again it's a conditional elimination. And there we go, now we're ready to list where we've got these from. So B or C is going to be a disjunction introduction from 12, and F or G is going to be from 11. And now all that remains is just to renumber some of the lines in my proof. So 13, 14, 15, 16, 17. We've already got the rules in for there. B or C and F or G, well that's just 13 and 14, and a conjunction introduction. A came from 1 and 15, and then this disjunction is from A, so 16. And there we go, there's our proof completed. So in that case, because the formulas are a bit more complicated to begin with, there was a bit more unpacking to do. Right, we built down to, I think it was line 8, before we looked any further, just to see what we could create. And that gave us some room to think about how we might get to our conclusion. So as I say, although we say work from the bottom of a proof up, I think it's also very useful to think about what we can produce from the beginning, from the premises that we have, and to almost work from both beginning and end towards the middle in the way that we've just done there. Okay, let's have a look at the final example then. Again, we've got quite long premises here. We've got H, and then we've got this long formula, 5 negation Z if and only if G or H and or F and H, and then H and H and H, or F then G then G. So again, let's start off by writing those in. H not Z if and only if 1, 2, 3 G or H or F and H, and 3 is H and H, oops, and H G, then G. And again, these are all premises, so let's mark them as such. And down on line Z, once more I'm going to write our conclusion, which is not Z and G and H. So let's start off again by thinking, how could we arrive at this conclusion? What rule would we have used to introduce it? Well, its main operator is a conjunction, so I'm going to say that it was a conjunction introduction. What would we have used? Well, we'll say that on lines X and Y we had not Z and G and H. And now, taking a step back again, where would we have gotten G and H from first? Well, in fact, we can see first of all that we'd need G and H, and our first premise is H. So it's going to come from 1. It's going to be a conjunction introduction again, being that that's its main operator. But we've already got one of the conjuncts, right? What we need on line W is G. Let's write that in white. So it would be 1 W, and that would allow us to introduce G and H. Now, as I did before, I'm going to concentrate on deriving G, and then I'm going to return to looking at how I got Z once I've completed that particular part of the proof. So, how might we have gotten G? Well, looking at our premises, it's the consequent of this conditional on line 3. So if we say it's a conditional elimination of line 3 and line V, then on line V all we need to get is H and H and H, or F then G. And going on again, we're going to think, well, how could we have gotten this? Well, looks like a conjunction introduction of H, which we already have. So again, line 1, and H and H, or F then G. There we go, and we'll say that that is line U. So 1 and U gave us H and H and H, or F then G. Okay, how would we have gotten U? Again, it looks like a conjunction introduction of line 1, and we'll say that on line T we had H, or F then G. Okay, where could we have gotten that from? Well, look, we've got H, so with a disjunction introduction we can get H, or F then G. So that would just be citing line 1 and our disjunction introduction rule. So we've already completed that particular part of the proof. We now know that's how we get G. Right? We can get the antecedent just from H alone. H goes to H, or F then G. That in combination with our first premise gives us H and H, or F then G, and again that in combination with our formula on line 1 gives us H and H and H, or F then G, and that is the antecedent of this particular formula here, and so that allows us to derive G, its consequent. Okay, now we can return to this question mark hanging over not Z. How would we have arrived at not Z? Well, looking at our premises, we've got Z here with 5 negations in front of it. So if we could get that on its own somewhere here, we could turn it first into not Z, and then into not Z. So let's say it's a negation elimination from line S. Let's use blue for that. So on line S we have not Z, and then on line R we have not Z. So on line S, this is going to have come as a negation elimination from line R, and line R is going to be a biconditional elimination from line 2, and we'll say Q, on which we would need the other half of that biconditional, which would be G or H or F and H. Now notice that we don't just jump from not Z to not Z, even though we can see that, you know, presumably 2 negations cancel out, then 4 negations will also cancel out, as we can see them doing. We have to move in 2 steps because our rule only allows us to get rid of 2 negations at a time. So that's what we're going to do. Sorry, that was a biconditional elimination, wasn't it? Okay, so now our question is, how could we have gotten to this? Well, we've already got one of the conjuncts. 1, it's going to be a conjunction introduction, being that that's the main operator. So we just need to know how we could have gotten G or H or F. So let's say that on line P we had G or H or F. Again, we've got a disjunction, so this is going to be a disjunction introduction. There we go. How would we have gotten to this? Well, now we're going to move. I'm going to move from the top down. So it's not. We're going to need one of these disjuncts. We're going to need either G or H or F. We don't have F anywhere in this formula other than where it occurs. In here it's kind of been introduced as a disjunction, so we can't get at the F there. It's the antecedent of a conditional, so that's no good to us. And here it's in the biconditional that we're trying to make use of, so that's no use. So it's going to be the H or G. Well, how can we get that? Well, let's look at our first premise. We've got H, and we know that our disjunction rule means that we can introduce anything in an OR statement with H, and it can come before it as well. So we can introduce G or H on line 4, and that's 1 and a disjunction introduction. And from there, of course, we can then introduce the F as another disjunct. So line 4 disjunction introduction gives us G or H or F. And there we go. We've again completed our proof. We've joined the top and bottom halves in the middle. So now I just need to go through once more and renumber these. So 5, 6, 7, so 15 in all. And remember, our proof isn't going to be complete until all of our rules have been written in correctly. So we got line 6 from a conjunction introduction of 1 and 5. We got not Z from a biconditional elimination from 2 and 6. We got not Z from line 7, negation elimination. We got H or F then G from 1 and disjunction introduction. Right, H is up here, just introduce that. Then we got H and H or F then G from 1 and 9. 1 and 10 gave us the next line, with both with disjunction, with conjunction introduction. Sorry. G we got from a conditional elimination of 3 and 11. 13 is our not Z, so that came from 8 and a negation elimination. G and H came from 12 and 1, 1, 12, and then finally not Z and G and H on lines 13 and 14 with a conjunction introduction gave us not Z and G or H. So there we go, there's some basic proofs just using the simple rules that we have above. So the rules I've introduced you to here, every symbol that we look at in PL has both an introduction and an elimination rule in for use in proofs. And here we've looked at the introduction and elimination rules for conjunction. We've looked at the elimination rules for negation, the conditional symbol, and the biconditional, and the introduction for our disjunction. Now, in the next few sessions, we'll look at the introduction rules for negation, conditional and biconditional, and the elimination rule for the disjunction. They're a little more complicated and they'll allow us to do some more sophisticated things in our proofs.